Hey, Premed's Adam here from the Premed Consultants. The video you're about to watch is a mock teaching session that I do with one of our TPC MCAT tutors, Xavier, who does a great job breaking down Newton's laws and static and kinetic friction. So this is actually a mock session that I was doing with him. I'm playing the role of a student, so it looks like I don't know anything about physics. That's why, although some of those terms definitely go years back at this point. But Xavier does a great job breaking down these concepts, and he does it from our Powerbook, the MCAT Powerbook. This is actually page 5 from the MCAT Powerbook, so enjoy the video.
Okay, so hi, thank you for joining us today. Today we're basically going to be talking about the beginnings of classical/Newtonian mechanics. And as part of that, we'll mainly be talking about friction, equilibrium, and just the different forces that can and often do act on objects and what that means for the object in total. So have you had a chance to look at any of the material that we'll be going over today?
Yeah, I think I briefly looked at some of it, but I didn't really study it in depth.
Yeah. And then did you have any preliminary questions about what you have gone over, or things that didn't make sense or you were slightly confused about?
I guess I was just wondering about do I need to memorize all these different formulas? Will it be provided to us on the actual test?
So they will not be provided to you on the actual exam on the MCAT, and so I don't really like to think about it as memorizing the equations, right? Because I think it's often helpful to understand the source of the equation, and then it helps you remember it better and for a longer period of time. And so we can actually go and start going through that. Would you say you have a grasp and understanding of the concepts themselves and just need help with the equations, or a little bit of both, or where would you say you're at in your mastery of any of these concepts?
I probably think I need a little bit of both. If we can kind of just start from square one, because I kind of remember this from physics, but not fully. So we can just break it down from the beginning. I think that'd be more helpful.
Okay, awesome. I'd be happy to do that. Okay, so when we first start talking about friction, as it states here, there's sort of two main types of friction. So when I say that one type of friction is sort of like this force that keeps an object from moving, essentially, right? It keeps an object's inertial mass at rest, if you will. What would you say? Does that sound more like static friction or kinetic friction?
Well, if it's keeping it at rest, you're saying in this situation, then I think it would be static friction.
Right. And then kinetic friction would be, sort of like a dynamic frictional force, right? Something that opposes the direction of an object's motion, right? That makes sense?
Yeah. So is that the friction that takes place when the object's actually in motion for kinetic
Correct.
friction? Okay, got
Correct.
it.
And so static friction, as I like to understand it, and is sort of linear, right? And so it's dependent on the force applied, or i.e. the magnitude of the force that's applied, and then like over a surface, essentially. And so when you're thinking about the equation for static friction here, it tells us that the static force is equal to mu sub s, which is just a subscript, if you will, to denote that it's the coefficient of static friction as opposed to kinetic friction. Because if you'll notice, it's very similar equations. Actually, it's the exact same thing, except the only thing that changes is the coefficient of, depending on if you're talking about static or kinetic, and then the normal force.
Got
And
it.
so from this equation, what can you tell me is sort of like a relationship that exists between any of the factors that are in this equation?
I guess if there's an increased mu, like the coefficient, then the overall friction is going to be more.
So I is the correct idea, right? Because the equation does suggest that there's a sort of direct relationship between the static frictional force and the coefficient of static friction or kinetic friction mu. But that actually doesn't happen because mu sub s is essentially a constant. And are you familiar with that term?
Got it. So you're saying it's going to be the same every single time?
No, right? So it's a constant as long as the surface stays the same.
Okay. What do you mean by that?
Does that make so? So the only difference between essentially what this equation is telling us that there is no dependence on surface area here, right? The static frictional force will stay the same as long as the two surfaces that we're analyzing remain the same.
Okay.
Right.
Right.
So it's
like
only
it'll
dependent.
so it'll change if it's a different surface or something, right? Like if you're
Correct.
on a carpet floor versus a desk table or something.
Correct.
Okay.
Exactly. Right. And it's and what I to clarify that it's not directly proportional as in terms of the normal force, right? So if for some reason we change the magnitude of the normal force, and can you think of a scenario where the normal force wouldn't exactly be equal to mg as we are typically thinking of it?
I'm not sure.
So do you remember inclined surfaces?
Oh, okay. So if it's like going up, then you're gonna have it because of when you're on the incline, it's you're not getting the full like
Correct.
180-degree vector.
Exactly, right? So when we're on an inclined surface, the magnitude of our normal force is actually equal to mg cos theta in most instances. And so that's an instance where, it's not, it will change depending on if you're on a horizontal surface or an inclined plane. And so that's what I mean by there's a direct proportionality between the static frictional force and the normal force, but not necessarily between the static frictional force and the coefficient of static friction.
Got it. So like what you're saying is that if the n increases or decreases, the f is going to increase or decrease.
Correct.
Proportionally.
Correct. And because of the nature of the equation and the similarities between static friction and kinetic friction, that same relationship applies as long as what?
Wait, sorry, can you repeat the question?
So I said that, what you just explained to me, right? That, that the static frictional force will increase with an increasing normal force or decrease with a decreasing normal force, right? That same relationship will exist for kinetic friction as long as the object is
moving, you're saying?
Correct. Exactly. Okay, so that is essentially the premise of the difference between static and kinetic friction. Now, there is a small caveat when it comes to static friction. And so, that's where in one instance is where this equation can sort of be misleading because the relationship between static and kinetic friction is actually discontinuous, right? And so I can try and draw a graph on here for you. Can you see that well?
Yep, I can see it.
So if we have our typical coordinate plane like so, y-axis here, x-axis here. This x is a function of the magnitude of the force applied. And then y-axis is a measure of static, or actually I should say, frictional force. Apologies for that. Oh, sorry. Just working out this thing. Okay, frictional force. What we actually end up seeing is with increasing force, there is that direct relationship I was talking about, right? And so essentially what I'm trying to do here is I'm trying to graphically illustrate what this equation is telling us essentially. And so with increasing force applied, we see a linear increase in the frictional force up to a certain point, right? And can you tell me what that point theoretically should be?
Well, when the friction force equals the force that's applied.
Correct. Exactly. Right. So the moment that forces exactly match, right, we reach a sort of maximal static frictional force. What we see is there's a sort of discontinuous function that starts, and now we start entering into. Can you finish that sentence for me?
I feel I know there's a word for it, but I'm forgetting what it is.
So we can go back, right? So if this is a function right here up until this point, it's a function of a force being applied and a resulting friction force, right? So this linear increase that we're seeing up to a maximum, what frictional force would apply at those points in time?
Oh, we're saying like this is static
Correct.
friction, and then it goes to kinetic friction.
Exactly. And so then our last point is from this graph, then we also see that the magnitude of the static frictional force, I can call it F sub S and then call this F sub K to clarify. The magnitude of the static frictional force is greater oftentimes than the magnitude of the kinetic frictional force. And then can you think of a reason as to why, or reasons as to why that would usually be the case?
I mean, I feel like it makes sense in theory, and then I'll try and get a reason for it. Because like for example, when I was at the gym, and my trainer yesterday, or was yesterday, it was like last week, was making me do like these sled pushes. So it was like this big heavy box, and basically getting it started was very difficult. Like it took a lot, and then once it was moving, like it was still, I could still tell there was resistance, but it was definitely less resistance. It was easier to move it. Is that kind of like an example of what you're talking about?
Right. So that's exactly it, right? And then that goes back to, sort of maybe something that was touched on earlier in the book about Newton's laws of physics and sort of like the law of inertia, right? Objects at rest will tend to remain at rest, right? Unless they're acted by a significant amount of force.
And objects in motion stay in motion.
Correct. And so what that usually tends itself to is depending on the surfaces that are at play here, which is why more or less the static frictional force is usually always greater than the kinetic frictional force, because of the coefficient of static friction, which is what that last point is getting to here in the book, where mu sub s is greater than mu sub s is greater than mu sub k, because usually more energy is required to uninertialize, if you want to think of that way, an object. Does that all make sense? Do you have any questions, or do you want me to clarify anything for you?
No, that was a really good breakdown. Thank you.
Yeah, of course, no problem. Okay. So then we can move on to equilibrium. Okay. So again, so what do you know about equilibrium and sort of, that difference between static and dynamic?
I'm not like I feel like as comfortable with this topic. I'm not really sure. Can you explain it?
Yeah, for sure. So the way I like to think of equilibrium is just, and it's a caveat way of thinking it, right? But I like to think of it relativistically at rest.
Okay.
And so static equilibrium is essentially when there is no motion in the object, whether that be translational or angular motion. And so when you're talking about static equilibrium, there is no net force acting on the object, right? And so what that essentially translates to, and sort of, I like to connect different ideas, right? And so if there's no net force acting on the object, then what does Newton's third law tell us about this object?
Not moving.
Correct. And more specifically, there's no acceleration of the object. And because of the relationship between position, velocity, and acceleration, that means that there's also no velocity on said object. And so that's essentially what this diagram is showing us here, right? So if we think of this object as being at rest, downward force being, what is an example of a downward pointing force that you know of?
Well, like someone pushing on an object from above. What do you mean by that?
So I just mean like a conservative force, for example.
Oh, like gravity?
Correct, exactly.
Okay.
Right. So we can think of this downward acting force in terms of gravity. So mg, and then typically the opposing upward acting force would be.
What's like the opposite of gravity? Well, I mean, if it's like the surface that it's on, right? So it's like it's kind of like the mass of the object. I'm not sure. What would the opposing force of gravity be?
That's actually a very interesting point that you bring up, right? Because it actually turns out that this opposing force, a normal force, right, the force that usually opposes the gravitational force when an object is at rest, is equal and opposite to
Right.
the force of gravity, and so it is, mg, because it's pointing in the opposite direction. It would be the opposite sign, and so this is typically thought of as the normal force.
Oh, right. That makes sense. So it's just like and then like in the opposite direction. So like how do you write that? Like negative F or something? Or
Yeah,
FN?
so
Okay.
yeah, right. So you can write it as FN, but I typically do this, but a lot of students don't really respond well to it. But I think of traditional coordinate system. And so if I'm to write, FG, like so, I'll typically write, and I usually put my nice little vector in front of it to know that it has directionality. I'll do equals negative mg to let me know that I've denoted down as the negative direction. And then by that logic, then Fn has to have the opposite magnet or opposite direction.
Right. So that equals mg.
Correct.
Got it.
But then typically students will like the idea of mg because negative is just too confusing, and will make the normal force the negative force. But you just have to keep that sort of directionality that you've chosen in your mind.
Got it.
But yes, right. So because these forces are equal and opposite, there is no net force acting on the object. The object experiences no acceleration, and therefore it doesn't move. Does that make sense?
Yep.
Awesome. So then we talk about dynamic equilibrium. Dynamic equilibrium brings into, in some instances, we'll bring in another concept of force, but we'll get to that in a little bit. And so what happens is there's also no net force acting on the object, which can be slightly confusing, right? There is also no
right, because it's like, can it be moving?
Correct. And as long as it moves, which is why I brought up the point of Newton's third law, right? Because Newton's third law tells us that the sum of forces will only account for an acceleration of an object, i.e. a change in velocity. And so as long as the object is moving with a constant velocity, it experiences no acceleration, and therefore it also falls into that Newton's third law paradigm. Does that make sense?
Yeah. Can we just quickly do the three laws, Newton's laws?
Yes, we can. So
I'm just trying to think of which one Newton's third law is.
Okay, so do you know what the three laws are and just don't know the order? Or
I mean, I know it's like an object at rest will stay at rest unless acted upon it. Every like force has or every action has an equal and opposite reaction. And then I think like the third law is like about acceleration. I'm not really sure how to word it.
Correct. So exactly, the exact same order. And so Newton's third law, written in its mathematical concept, essentially will be that the sum of the forces that are acting on an object, and so when it gets to be more sort of like torque and everything like that, you start to see that because these are vectors, it's really, the vectorial sum of all the forces, right? So it can be really nice sometimes when you see a force that's acting at an angle to break down all the forces in terms of their X and Y components. And so you'll see, throughout the instruction, throughout the course, that I typically like to put the little vector symbol on top of all my vectors to remind me that, oh, I always need to consider that there's an X and Y component to this force.
Got it.
And so that's going to be then, the sum of all the forces And then you heard me say like the net force, right? That's essentially the sum of all the forces. It's the same sort of.
Right. Yeah. That makes sense.
Is going to be equal to the mass of that object times the acceleration.
Okay.
And the acceleration, actually, if you notice, is also a vector.
Right. Yeah, because
And
you can
so,
be accelerating in a direction. And then that's why, just so if the net of all the forces is 0, the acceleration is going to be 0.
exactly. And so if there can be no acceleration on an object and the object is at rest, or there can be no acceleration on the object and the object is in motion, but with a constant velocity.
Got it.
And so that's where you get that difference between static and dynamic equilibrium. And so kind of tying this in then to our next concept, and you notice that this last bullet says, so if the system's not equilibrium, the center of mass is accelerating translationally and or its parts are accelerating rotationally.
Hope you enjoyed that quick 20-minute segment from the MCAT Powerbook. If you are enjoying the content and want more free MCAT content, don't forget to like and subscribe. And if you want your very own MCAT Powerbook, then you can click the link below and purchase a copy.